Good morning, students, and welcome to the physical chemistry lecture. Let us begin with the proper syllabus of the chapter 4, that is solution. In the introductory part, you have studied the definitions of common terms that are often used in the study of this chapter and the different concentration units. So our second point, it is the ideal solutions, Raoults law, vapor pressure of ideal and non-ideal solutions of miscible liquids. And miscible liquids means in the formation of formation of a solution when two liquids they get completely miscible into each other. For example, acetone, ethyl alcohol, or any two organic liquids, they are completely miscible into each other. Then the third point of this chapter, it is composition of liquid and vapor pressure and the boiling point, diagrams of miscible liquids, distillation behavior of liquid pairs of type 1, type 2 and type 3. We see one by one in detail at that time. And the next point of this chapter, it is the solubility of partially miscible liquids. And again, depending on the miscibility or solubility of partially miscible liquids, there are three different types of solutions, and that are the solutions with minimum CST. CST, that is the critical solution temperature, and it is defined as the temperature at which two completely immiscible liquids they becomes completely miscible, and that temperature is termed as consolute temperature or critical solution temperature, and it is abbreviated as CST. And the last point of this chapter, it is the vapor pressure and distillation of immiscible liquids and steam distillation, fractional distillation, etc. We see one by one later on. Then remember these two names of the scientists, William Henry and the Francis Mary Raoult. Remember well, these two scientists, they studied a lot with the vapor pressure of liquids and solutions. Then Henry's law, though it is not for your syllabus, but you should know it. Here, the concentration of a dissolved gas in a solution is directly proportional to the pressure of the gas above the solution. I repeat once again, Henry's law, the concentration of a dissolved gas in a solution is directly proportional to the pressure of the gas above the solution, and mathematically it is given by C, it is equal to K into P, where C, it is the concentration, K, it is the constant, and P, it is the pressure. This law applies most accurately for dilute solutions of gases and do not dissociate gases, they do not dissociate or react with the solvent. The Henry's law, it is applicable to the CO2 gas, N2 gas and O2 gas, and it is not applicable to the HCl and HI gases. Then this is the first point of our chapter. Here, Raoults law, ideal and non-ideal solutions. So, I will explain you at first what is the Raoults law. Here, the Raoults law states that partial vapor pressure of any volatile component of a solution at any temperature is equal to the vapor pressure of pure component multiplied by the mole fraction of that component in the solution. And simply remember that the partial vapor pressure of any volatile component of a solution at any temperature is equal to the product of vapor pressure of pure component multiplied by the mole fraction of that component in the solution. And this law, it is explained as follows. Suppose we have a binary solution, and our binary solution, it is made up of solution uh, contains liquid A and liquid B, and Na, these are the moles of volatile liquid A, and Nb, these are the moles of volatile liquid B. And if Pa and Pb are the partial vapor pressures of two liquid components, then mathematically, according to Raoults law, we can write here the vapor pressure of solution, that means Ps, it is equal to, this is the mole fraction of solvent, and this P0, it is the vapor pressure of the solvent in a pure state. This is the general mathematical expression of Raoults law. The vapor pressure of any pure partial vapor pressure of any constituent of the solution, it is the mole fraction of that constituent multiplied by the vapor pressure of that constituent in a pure state. Here P, yes, that means P solution, it is equal to observed vapor pressure of the solution, then X into solvent, that is the mole fraction of the solvent, and P0 solvent means the vapor pressure of pure solvent. Here, when the liquid vapor pressure behaves ideally, then according to Daltons law, the total vapor pressure of the solution, that means P total, it is equal to sum of two partial pressures of the constituent A and constituent B. Here, PA, it is equal to XA into P0A, where XA, it is the mole fraction of pure constituent A, and P0A, it is the vapor pressure of the constituent A. Similarly, partial vapor pressure of constituent B, it is equal to XB into P0B, where XB, it is the mole fraction of constituent B, and P0B, it is the vapor pressure of pure B. Here P0 is the vapor pressure of the pure solvent. Here this P0, it denotes the vapor pressure of A constituent. So we have put here A, and this is the vapor pressure of pure B. Therefore we have written B here. And this PA and PB are the partial vapor pressures. Simply remember that according to Raoults law, partial vapor pressure of any constituent, it is the product of vapor pressure of that constituent in the pure form multiplied by its mole fraction. And according to Dalton's law, the total vapor pressure of the solution, it is the sum of partial pressures of the two constituents. So we can write the modified Dalton's law as P total, that means total vapor pressure of the solution, it is equal to PA plus PB, and it is equal to XA into P0A plus XB into P0B. And if we plot the graph of vapor pressure versus mole fraction, here if we plot the graph of vapor pressure here on the y-axis, and on the x-axis suppose we have mole fraction. Then for constituent A we have, this is the straight line graph. Here we have, this is the straight line graph, and this is the straight line for component B. That means at this point we have XA, that means mole fraction of A constituent, it is equal to unit, and at this point here we have mole fraction of A constituent, it is equal to 0. Then as mole fraction of A constituent increases, the vapor pressure of A constituent it also increases, and it is the limiting value, and this value it is termed as the vapor pressure of pure A constituent. Similarly, at this point we have the mole fraction of B constituent is 0, and here the mole fraction of B constituent is 1. Therefore, as the concentration or mole fraction of B constituent increases, the vapor pressure of B constituent increases, reaches to a maximum value, and this maximum value we call as the vapor pressure or partial vapor pressure of B constituent in the pure form. And this is the equation of Raoults law, and it is equal to the partial vapor pressure of A constituent, it is equal to here vapor pressure of A constituent in the pure form multiplied by the mole fraction of A constituent. Here any point on this line, it gives the partial vapor pressure, and it is the product of P0A into XA. Similarly for B constituent, that means here we get a straight line equation, and this is the total vapor pressure line. When we join these 2 points P0A and P0B, we get total vapor pressure line, and it is the sum of partial vapor pressure of A constituent plus partial vapor pressure of B constituent. And the ideal solution is the solution which obeys the Raoults law at all conditions of temperature and concentration. Remember well, the ideal solution is defined as the solution which obeys Raoults law at all conditions of temperature and concentration. And the condition of Raoults law, that is the graph of vapor pressure versus mole fraction. This graph it must be straight line. Here this graph it must be straight line. Here our solution it obeys Raoults law. Therefore we get for A constituent as well as for B constituent, these are the two straight lines. Therefore our solution is ideal solution. And the definition of non-ideal solutions, that is the solutions which do not obey the Raoults law at all conditions of temperature and concentration. Such solutions are called as non-ideal solutions or real solutions. And in case of real solutions, instead of getting straight line, we get a curved lines. Here we get a curved lines, and it is shown in the next picture. Here the Raoults law for ideal solutions. A solution that obeys a Raoults law is called as a ideal solution, and for ideal solution we have the graph of vapor pressure versus mole fraction. These are the straight lines, remember well. And here the non-ideal solutions, they do not obey the Raoults law. Therefore we get a curved line. instead of getting straight line, we get a curved line. And all these solutions we called as a non-ideal solutions. Here, if we have A constituent and B constituent, and these two are real solutions or non-ideal solutions. As we have seen earlier, when we plot the graph of vapor pressure versus mole fraction, and when the solution behaves ideally, then we get this straight line, and for non-ideal solution we get this type of curved line. This blue line, it is for non-ideal solutions. Similarly, here also we have, this is a curved line, and this is also a curved line. This is for non-ideal solution or real solution. And the ideal solutions, we get a straight line. These green lines are straight lines. They are the ideal solutions. In this diagram, we have shown the Raoults law for ideal solution and for non-ideal solution. Remember well. Then the negative deviation and positive deviation from the Raoults law. As already we have seen, the real solutions, they deviates from the ideal behavior when the curve is below the straight line. Here all these curves are below, we have seen here, and this is the negative deviation, and this is a positive deviation from Raoult's law. A weak solute-solvent interaction results in a vapor pressure higher than predicted one, and here the exothermic mixing, it is equal to positive deviation. Here these curved lines are above the ideal straight line, and such type of deviation, it is termed as positive deviation. In detail we will see later on.